This is a lecture on reactions of alkenes that I gave on June 11, 2020. Electrophilic addition reactions are common reactions of alkenes, and they proceed through carbocation intermediate. So here is an example of an electrophilic addition reaction. That's a reaction that involves addition of hydrogen bromide to simplest alkene ethene. Reaction mechanism is shown here. So the first step is a slow step. It involves addition of the electrophile, and in this case electrophile is proton, but proton does not appear on its own. In this case we have hydrogen bromide, a covalent compound. So this is not ionized bond, and hydrogen actually acts as a proton, even though on its own this hydrogen is not a proton. It is an electrophile. Hydrogen-bromine bond is polar bond, and hydrogen is electron deficient. So it accepts free electron pair from a pi bond, as shown by curved arrow, and that causes hydrogen-bromine bond to break. That's the first slow step. It involves formation of carbon-hydrogen bond and a corresponding carbocation. It also, as a result of breaking of hydrogen-bromine bond, results in formation of bromide anion, a nucleophile. This is a slow step because it involves charge separation. So positive and negative charges are separated from each other. That's thermodynamically not favorable process, and it is a slow step. Second step is fast step. It involves only bond formation, and in this case positive and negative charges combine to give neutral product. So bromide anion, in this case bromide anion is the nucleophile. So in the second step, nucleophile reacts with carbocation, donates its free electron pair to form a bond with carbocation, and that results in formation of the final product. In this case, bromoethane is the final product. And underneath, there is reaction in general terms. So frequently, reagent is not ionized. Instead, it's one where electrophile and nucleophile are attached to each other by covalent bonds. Alternatively, of course, electrophile and nucleophile could be separated in form of ionic compound. And you can see the same mechanism in general terms. We can infer that carbocation is the reaction intermediate from several observed phenomena. First is loss of stereochemistry in the product, which means that both cis and trans isomer of an alkene, if starting alkene is capable of cis-trans isomerism, both cis and trans isomers give the same product. Secondly, reaction rates are related to stabilities of the intermediate carbocations. And finally, reaction rates are higher in polar solvents due to stabilization of the transition state as a result of formation of the intermediate carbocation. When we consider stability of carbocations, first we should classify carbocations. Carbocations are classified as methyl. Obviously, that one is generated from methane. Primary is carbocation where electron deficient carbon is attached to one more hydrocarbon substituent. Secondary, where electron deficient carbon is attached to two more hydrocarbon substituents. And tertiary, where electron deficient carbon, carbocationic carbon, is attached to three hydrocarbon substituents. And here we have the order of stability of carbocations. We can see that tertiary carbocation is the most stable, then secondary, then primary, and the least stable is methyl. And so reaction rates follow the order of stabilities of these carbocations. Addition reaction that involves tertiary carbocation will be the fastest, while one that involves primary will be the slowest. Of course, there could be no methyl cation involved in reactions like these because methyl cation is on its own. Methyl cation cannot be part of original double bond. So primary carbocation would be, so reaction involving primary carbocation, as in example above, would be the slowest reaction. Observed stability of carbocations is explained by electron delocalization, and this is a special case of electron delocalization called hyperconjugation. Hyperconjugation involves delocalization of electron pair from sigma bond. So when we consider a carbocation, you can see that a carbocationic carbon is sp2 hybridized and has three substituents. And on that carbon there is of course an empty p orbital, empty p atomic orbital. So now when we consider individual carbocations, for example, this is a primary carbocation, and in primary carbocation we of course have empty atomic p orbital, so that's obvious here. And then on the neighboring substituent we have one carbon, in this case carbon hydrogen sigma bond, and that's this bond right here. So this carbon hydrogen sigma bond that is properly aligned for electron delocalization. You can see that it's in the same plane as atomic p orbital that is empty, so electron pair delocalizes, basically spills over from sigma bond into empty atomic p orbital. Electron delocalization stabilizes carbocation for two reasons. One is that now that electron pair from sigma bond has spread into additional region of space, two electrons that form that electron pair are further apart from each other, and that minimizes electrostatic repulsion. The other reason, even more important reason, is that electron delocalization into the empty atomic p orbital reduces electron deficiency of the carbocationic carbon atom. So this is much more stable than if there was no hyperconjugation. But as you can see, in each substituent, only one sigma bond is properly aligned for electron delocalization through hyperconjugation. These other two bonds are not aligned for electron delocalization. Now, when we consider secondary carbocation, you can see that there are two such bonds, two substituents, so one from each. There are two such bonds that are properly aligned for electron delocalization through hyperconjugation. That means greater degree of stabilization compared to primary carbocation. And you would expect that secondary carbocation would be more stable compared to primary. And finally, tertiary carbocation would be the most stable, because now electron delocalization through hyperconjugation is maximal. Is at maximum because we have three substituents, and so there are three carbon-hydrogen bonds that are delocalized through hyperconjugation. We can't have more than that, so that's the maximum amount of stabilization. So we would expect that the order of stability would be tertiary carbocation is the most stable, and then secondary, and least stable would be primary carbocation. And of course, methyl carbocation is even less stable than primary. And the reason why it's less stable than primary is that it has no substituents. So there are no sigma bonds on hydrogen that could donate electron density into the empty atomic p orbital. Next, we are going to examine regioselectivity of addition, electrophilic addition to an alkene. So, in general terms, if starting material A reacts in such a form that in such a manner that it can give two possible products, B and C, and B and C are regio isomers, not just structural isomers, but regio isomers, it's a form of structural isomerism, then reaction may or may not be regioselective. If B and C are formed in statistically expected ratio, then reaction is not regioselective. But if one product is formed in higher amount than expected and one lower than expected, then reaction is regioselective. So let's consider addition of hydrogen halides. So in case of, for example, addition of hydrogen chloride to 2-methyl propene, there is possibility for formation of two products, 2-chloro, 2-methyl propane, and 1-chloro, 2-methyl propane. Statistically, we would expect chlorine atom, that's what is easy to follow from molecule of HCl, so we would expect chlorine atom to add with equal probability to carbon 1 of the double bond and carbon 2. And so we would expect two products to form in 50-50 ratio, 50% each. But that's not the case. We get more substituted product as the major product, and less substituted is minor. So this reaction is regioselective. And regioselectivity is given by Markovnikov rule. Markovnikov formulated his rule as empirical rule in 19th century before mechanisms were known, because carbocations were known. He simply did a large number of reactions and formulated rule based on them. So according to Markovnikov rule, in an addition of hydrogen halide or water to an unsymmetrical alkene, the hydrogen, or in general the electrophile, adds to the carbon of the double bond that is bonded to more hydrogens. At the time, of course, Markovnikov had no idea why that rule worked. Now we know why it works. Because when you consider reaction mechanism, hydrogen could add to carbon that contains more hydrogens. This is the carbon of the double bond that contains two hydrogens, or one that contains fewer hydrogens. Addition of hydrogen to carbon that contains more hydrogens results in formation of, in this case, secondary carbocation, more stable, more substitute carbocation. On the other hand, addition of hydrogen to carbon that contains fewer hydrogens results in formation, in this case, of primary carbocation, less stable carbocation. And of course, the reaction is going to proceed to more stable carbocation, preferentially to give more substitute product. And we can see that from reaction diagram that formation of carbocation is an endothermic reaction. And being endothermic, there is late transition state. So transition state involves, or transition state resembles the product, in this case carbocation. So transition state that leads to formation of secondary carbocation, because it resembles secondary carbocation, is more stable compared to transition state that leads to formation of primary carbocation. Secondary primary carbocation, which means that formation of secondary carbocation is both thermodynamically and kinetically favored. These reactions, by the way, are kinetically controlled. Here are some examples of Regio selectivity of electrophilic addition of hydrogen halides. So in this first example, addition of hydrogen iodide to 2-methyl 2-butene results in formation of 2-iodo 2-methyl 2-butene as the major product. That's of course because carbon 2 of the double bond has no hydrogens. Carbon 1 has one hydrogen. So we follow Markovnikov rule. Hydrogen atom adds to carbon with fewer hydrogens to give, in this case, tertiary carbocation, and tertiary carbocation then combines with iodide nucleophile to give 2-iodo 2-methyl butane as the major product. Don't be confused by rings. Cyclic compounds react the same way. So in this example, where you have 1-methyl cyclohexene, addition of hydrogen bromide occurs in such a way that hydrogen adds to less substitute carbon. That's carbon that contains more hydrogens. That's carbon 2. It contains one hydrogen. Carbon 1 contains no hydrogens. So addition of hydrogen to carbon 2 gives again tertiary carbocation to give as major product 2-bromo 2-methyl cyclohexane. Since carbocations are the reaction intermediates, and carbocations differ in stability quite a lot, so tertiary being the most stable, then primary, then secondary, and then primary, rearrangements are common. So these reactions frequently proceed with rearrangements. Rearrangements means that there is an intramolecular reaction where one group undergoes a shift. And typical rearrangements involve hydride shift, that would be 1,2 hydride shift from the neighboring, from one carbon to next carbon, or 1,2 alkyl shift of the alkyl group. So here is the mechanism. So if you have carbocation in a molecule, neighboring hydrogen could shift. So it takes its electron pair and shifts to the carbocationic carbon. So with its electron pair. That's why it's called hydride shift. This is a transition state. So it's not an intermediate, it's a transition state where hydrogen temporarily forms a bond with both carbons, and then in the final product, hydrogen has fully formed bond that used the original carbocation, and carbon that hydrogen has left is new carbocation. The same mechanism operates with alkyl groups. So we have alkyl shift, where alkyl group shifts, and again, same outcome and same mechanism. As a general rule, the smallest group undergoes a shift, which means hydrogen preferentially to methyl group, methyl preferentially to ethyl, ethyl preferentially to propyl, and so on. Here are some specific examples. So this is addition of hydrogen chloride to 3,3-dimethyl-1-butene. So first step is protonation to give secondary carbocation. Now, based on mechanism you learned so far, you may expect that chloride anion would donate electron pair to form a bond with carbocation and form the product, 2-chloro-3,3-dimethyl-butane. But actually, that's only minor product. Typically, it forms in about maybe 3% yield. Major pathway involves methyl shift. So one of these three methyl groups, any one of these three methyl groups, shifts to the carbocationic carbon, and that results in formation of new tertiary cation. So you see we went from secondary to tertiary carbocation. And now electrophile, chloride anion, adds to tertiary carbocation to give the final product. And now that product has rearranged carbon skeleton. So it's 2-chloro-2,3-dimethylbutane. So always watch for possibility of rearrangement, particularly when intermediate is secondary carbocation and also primary. Always look for possibility of rearrangement into more stable tertiary carbocation. Now be careful because sometimes there are no rearrangements, at least first approximation that we consider in this course. So in an example like this, the actual systems are much more complex, but we'll just assume a simplest example. So example like this, 4-methyl-1-pentene, addition of hydrogen bromide results in formation of secondary cation. Now, hydride shift, rearrangement of hydrogen from carbon 3 to carbon 2, results in formation of another secondary carbocation. So you should assume that in this case there is no rearrangement and only unrearranged product is formed. In case of rings, and that's 3-membered ring and 4-membered ring. Cyclopropyl and cyclobutyl rings, rings undergo ring enlargement. So in the course of rearrangement, for example, a 4-membered ring is enlarged into 5-membered ring and 3-membered ring into 4-membered ring. So remember that for ring compounds. Rearrangements of 5 and 6-membered rings tend to get rather complex, but in general you should treat them as open chain compounds and simply assume that secondary carbocation rearranges into a tertiary. In some cases, addition reaction to an alkene can proceed through free radical intermediates. And that's generally the case if addition of hydrogen bromide is carried out in the presence of an ether as a solvent. So typically we use solvents such as dichloromethane, and those are typical ionic conditions as shown here. And then addition is, as you would expect, Markovnikov addition, because reaction proceeds to carbocation, and so the most stable carbocation is the reaction intermediate. But if reaction is carried out in diethyl ether, then at first glance somewhat unexpected reaction occurs because the major product is less substituted haloalkane, bromoalkane. So in this case, reaction of 1-butene results in formation of 1-bromobutane. The reason for that is that ethers, including diethyl ether, contain peroxides as impurities, and so peroxides serve as radical initiators. Under ordinary conditions, even visible light will decompose a peroxide. Here are some typical peroxides. So hydrogen peroxide is here, shown here, and this is dialkyl peroxide. Something like alkyl hydroperoxide is also something that could be present in a solution. This would be ROOH. In all of those cases, there is this weak oxygen-oxygen single bond. That bond can be easily homolytically broken to give free radicals. And it's broken, as I said, even with the presence of a visible light. That's actually what makes ethers unstable and sometimes dangerous to store, formation of peroxides. In addition of hydrogen halide to an alkene, these peroxides could act as initiators and cause reaction to proceed through a free radical reaction mechanism. And so, as in any free radical reaction, first we have initiation steps. Those are steps that generate free radicals. So those would be steps where peroxide is decomposed or oxygen-oxygen bond is broken into hydroxyl or alkoxyl radicals. Now those radicals react with hydrogen bromide to form corresponding alcohol. When hydrogen bromine bond is homolytically broken, a radical that forms more stable bond with oxygen is the one that reacts with oxygen, and that's hydrogen to form alcohol. Obviously, oxygen-bromine would be less stable. And that results in formation of bromine radical. So that's the outcome of the initiation step, formation of bromine radical. Next, in propagation step, this bromine radical adds homolytically to carbon-carbon pi bond. So carbon-carbon pi bond is broken homolytically. One electron pair pairs up with one free electron pairs up with electron of bromine to give carbon-bromine bond, and the other remains as free radical on the far carbon of the double bond. That free radical electron, that's now carbon radical, reacts with another molecule of hydrogen bromide to cause homolytic breaking of hydrogen bromine bond. So hydrogen with its free electron pair pairs up with carbon electron to form carbon hydrogen bond, and that regenerates bromine radical. And this bromine radical now can go back into first propagation step, and then this reaction keeps on cycling over and over again. So those are two propagation steps. Reaction keeps going until for as long as there is enough material. Once we run out of starting material, termination steps occur. But this is one very important termination step, formation of dimers. As you know, formation of dimers is an indication that mechanism is free radical. Other products that have also been observed are formation of dibromide and formation of bromine itself. We explain free radical mechanism by so-called peroxide effect. As it is interesting that hydrogen bromide readily reacts under free radical conditions. So hydrogen bromide will readily add under free radical conditions. On the other hand, hydrogen chloride and hydrogen iodide don't. In fact, hydrogen iodide never reacts under free radical conditions. Hydrogen chloride may react, but it's not very common. So what's the reason for that? So under peroxide effect, we would look at two propagation steps. When we consider thermodynamics of radical reaction, we consider only the two propagation steps, because those are actually the steps where reaction is occurring. Initiation steps serve to start the reaction and terminations to end it, but actual reaction occurs during propagation steps. So here we consider two propagation steps, first and second propagation step, and here is enthalpy of each step. In case of addition of hydrogen chloride, we can see that second propagation step is endothermic. That's unfavorable, because if free radical forms, then termination step is always exothermic because it involves only bond formation. So if here second propagation step is endothermic, then termination will occur preferentially to second propagation step, and so in case of chlorine, in general, this reaction cannot propagate. So for that reason, even in the presence of free radicals, hydrogen chloride will add through ionic mechanism, and reaction outcome will be more comical. In case of bromine, we can see that both steps are exothermic, both are favored, and that's why addition of hydrogen bromide readily occurs and proceeds through free radical reaction mechanism. Finally, in case of hydrogen iodide, addition of hydrogen iodide, we can see that first propagation step is endothermic and cannot occur. Second would have been very favorable, highly exothermic, but first cannot occur. So simply that's because carbon-iodine bond is weaker than carbon-carbon pi bond. And as this step does not occur, then by default hydrogen iodide always adds through ionic mechanism. So from this we can draw a conclusion that in general only addition of hydrogen bromide occurs through a free radical mechanism when conditions are appropriate. That means either use of ether as a solvent, or if we add peroxides as radical initiators. And we should then consider stability of free radicals. So stability of radicals is important because we have seen that reaction mechanism is anti-Markovnikov. And so why would that be the case? Well, that's because first step involves addition of bromine, and that means that initial addition results in formation of carbon radical, and the most stable carbon radical will form. More substitute carbon radical is more stable, as you can see from this diagram. So tertiary radical is the most stable, then second most stable is secondary, and then primary. And since this is endothermic reaction, we have late transition states, so their stabilities resemble stabilities of the corresponding radicals, which means the tertiary radical is both kinetically and thermodynamically favored product, then secondary, and finally primary. So that means that bromine in the first propagation step will preferentially add to less substrate carbon. Carbon contains more hydrogens because that results in formation of more stable, more substrate free radicals. Now, why are more substrate radicals more stable? The reasons for that are twofold. The main reason is in steric hindrance. For example, tertiary radical has 3 large alkyl substituents, which on sp3 hybridized carbon are relatively close to each other, and there is steric hindrance between them. If free radical is formed, we go from an sp3 hybridized carbon, which is tetrahedral, to an sp2 hybridized carbon. And now these 3 substituents are further apart from each other, and so steric hindrance is minimized. So formation of a radical reduces steric hindrance, but the more substituents there are, the more hindrance is released or reduced. In case of primary radical, there isn't much steric hindrance to start with, and so formation of radical does not result in as much stabilization. So the main reason for stability, for increased stability of tertiary radical over secondary and secondary over primary, is in steric hindrance. So reasons are steric. So you can see that both free radicals and carbocations exhibit same order of stability. That would be tertiary, secondary, primary, methyl, but for different reasons. In case of free radicals, reasons are steric, while in case of carbocations, reasons are electronic. And so here is the order of stability. So tertiary, secondary, primary, methyl. And more hindered free radicals also have longer lifetimes, and that's due to steric hindrance of the approach of the reagent. And you can see it here. In case of methyl radical, reagent can easily approach radical and combine with the free radical to give the product. On the other hand, in case of tertiary radical, this reagent will interact with substituents and bump into those substituents. So it's going to have difficulty interacting with the free radical. And so for that reason, more substituted free radicals such as tertiary radicals have longer lifetimes compared to less substituted free radicals, which of course also makes them more stable. Now we're going to look at reactions that proceed through a cyclic intermediate or cyclic transition state. And one of the best known reactions is addition of halogens, specifically addition of bromine. So in such reaction, an alkene reacts with bromine to give a dibromide, and that dibromide is known as vicinal dibromide. Word vicinal means that substituents are on the neighboring carbons. This reaction is often used as diagnostic reaction for presence of double bonds, or in general for presence of pi bonds, because bromine adds across a pi bond. And this is visually very easy to follow reaction. Bromine is dark red-brown liquid, and product is colorless. So disappearance of color of bromine is an indication of positive reaction. It's an indication that reaction is occurring, and in fact we can even carry out titration and find out how many equivalents of bromine have been used up, and that means how many pi bonds are present in a molecule. Here, reaction mechanism is shown with accompanied reaction diagram. So initially, an alkene and bromine react. Bromine is the electrophile, and that's because of the empty d orbital of bromine. So empty d orbital accepts a pi electron pair, and that will cause bromine-bromine bonds to break. Now note that in this case, carbocation is not the intermediate. Carbocation is a transition state. You see the top of the energy diagram. So carbocation is a transition state, and the actual intermediate is cyclic bromonium ion. So that's shown right here. That's the actual intermediate. So you see three-membered ring with positive charge on bromine. That's cyclic bromonium ion. And then backside attack results in formation of vicinal dibromide. And note that backside attack results in formation of, in case of cyclic compounds, trans disubstituted cyclic compound. So this is trans 1,2-dibromocyclohexane. Now the addition is anti. Anti, so that's anti-addition. Anti means that addition is from the opposite sides of double bond. So two substituents, two bromines, add from the opposite sides of double bond. Product is trans. So don't mix up those two terms. Don't call this trans addition, that would be wrong. Product is trans, but addition is anti. And I already mentioned that products are vicinal dibromides. That means two bromine atoms are on the neighboring carbons. If, as in this case, two bromine atoms are on the same carbon, or two substituents are on the same carbon, that's geminal compound. In this case, geminal dibromide. Another reaction that proceeds through cyclic transition state or cyclic intermediate. Previous also proceeded through cyclic intermediate, bromonium ion. So this one that proceeds through cyclic intermediate is oxymercuration, and that's followed by demercuration step. So oxymercuration means addition of oxygen and mercury. So in an oxymercuration reaction, an alkene reacts with mercury species, mercuric acetate. So this is mercuric acetate in suitable solvent. Solvent is mixture of water and tetrahydrofurane. Water is needed as a reagent, that's that oxy part, addition of oxygen, and THF is tetrahydrofurane, that's organic solvent that is miscible with water and is used to dissolve organic compound substrate because alkenes are not soluble in water. On the other hand, mercuric acetate is soluble in water. So initial step is oxymercuration reaction, so oxy, addition of oxygen and mercury. It's oxymercuration. Second step is demercuration step, and that reaction is carried out with sodium borohydride. In presence of aqueous solution, we add small amount of potassium hydroxide just to stabilize sodium borohydride. Sodium borohydride is complex metal hydride, and it behaves as if it were hydride anion, H-. So it's actually a source of H-. And so that results in replacement of mercury with hydrogen. So as you can see, net result of addition, net overall result is addition of water across a double bond. One nomenclature point, acetate, abbreviation is OAC, is this species, OCOCH3, so that's acetate. Don't mistake that for acetyl. Acetyl is abbreviation AC, and that's COCH3. So acetyl O is acetate. Here is the reaction mechanism. So in aqueous solution, mercuric acetate is dissociated, and of course only one dissociation occurs to give mercury plus and acetate minus ions. Loss of second acetate anion is unlikely because that would mean loss of negatively charged anion from species that is already positive, and that's thermodynamically not feasible. So this is electrophilic mercury, electron deficient mercury. So in the first step, this mercuric cation adds across the double bond, so pi electron pair adds to mercury, and we end up with cyclic mercurinium ion. Note it's similar to bromonium ion we have seen before. And then backside attack of molecule of water from the opposite side results in oxymercuration. So this is oxymercuration product. It's an oxonium ion, so loss of water to a base, and this acetate anion that is a result of dissociation of mercuric acetate is actually suitable base, so acetate anion picks up a proton and leaves as molecule of acetic acid. So this is final product, result of oxymercuration. You don't need to know the mechanism for the second step, but so in this reaction, hydride anion displaces mercury to give the final product. Here are some additional examples. Note that when a double bond is unsymmetrical, addition is Markovnikov addition. So the final product is result of Markovnikov addition. So hydroxyl group ends up on the more substituted carbon of the double bond, and hydrogen or less substituted carbon, even though carbocation is not involved. The reason for it is in carbon-mercury bond strength. So more substituted carbon forms weaker bond to mercury, and that's where reaction occurs. Of course, free electron pair from oxygen is added to antibonding carbon-mercury orbital. That's antibonding carbon-mercury orbital. And since this is weaker bond, then this orbital has lower energy compared to alternative, this other carbon-mercury bond. So this orbital has lower energy, and that's when it accepts free electron pair. So that's why addition is Markovnikov. There are no carbocations as reaction intermediates. It simply has to do with carbon mercury bond strength and orbital energies. So free electron pair from oxygen adds to lowest energy orbital, which is a more substituted carbon-mercury bond. Here we have another example, and third example all show that more substituted alcohol forms. Now, sometimes the question is, why would we want to carry out oxymercuration, demercuration? We can simply add water across a double bond by mixing alkene and water and adding a drop of an acid catalyst like sulfuric or phosphoric acid. So why we would want to use toxic mercury and then carry out two-step process? Well, there are some advantages. First, reaction is much cleaner. In case of acid catalyzed reaction, even though Markovnikov rule is followed, we get two isomers, more and less substitute alcohols in maybe 70, 30, 80, 20% ratio. And that's not very good. Even though we get predominantly one isomer, still we get a lot of other, and they may be difficult to separate. And in any case, that reduces the yield of desired isomer. In case of oxymercuration, demercuration, we get much better yield of desired alcohol. And another reason is that if you start with an alkene like this one, 3,3-dimethyl-1-butene, which could possibly undergo rearrangements, under acidic conditions, reaction will be accompanied by rearrangement because carbocation is reaction intermediate. So we get rearranged product. But under oxymercuration, demercuration conditions, we don't get rearranged product because carbocation is not reaction intermediate. So by carrying out oxymercuration, demercuration, we avoid rearrangement and have straightforward addition of water across double bond with oxygen ending up on more substitute carbon of the double bond. The third reaction in this class is hydroboration oxidation reaction. Hydroboration is a concerted reaction, which means it does not proceed through an intermediate, but it does proceed through a cyclic transition state, and that's why it belongs to this class. Reagent for hydroboration is borane. Its formula is BH3, and if we draw a structural formula, so that's boron attached to 3 hydrogens through single bonds. From this formula, you can tell that boron is a coordinately unsaturated compound. It has only sextet of electrons, not octet. It has one empty orbital, and so it is relatively unstable compound. Now, under ordinary conditions, it exists in form of diborane, which means that two BH3 molecules dimerase to form a diborane molecule. This is diborane molecule of rather unusual structure. These bonds, BH bonds on boron, are ordinary bonds, typical sigma bonds. But you can see that there are these bridged bonds, what we call banana bonds. So this is one, and this is the other. So these bonds actually have, even though they have 3 atoms, so boron, hydrogen, boron, so even though there are 3 atoms there are only 2 electrons. So it's actually boron-boron bond with 1 electron pair with proton embedded in the middle. Very unusual bond, and same here. So boron-boron bond with proton in the middle. So 1 electron pair connects 3 atoms, where we would usually have 2 bonds and 2 electron pairs. So there are a total of 2 electron pairs, 1 for the top bond and 1 for the bottom bond. And that, in a way, satisfies electron deficiency of boron. Usually we use borane in an ether as a solvent, and then ether is electron pair donor, and we end up with complex, like in this case, boron THF, tetrahydrofuran complex, and then that's the reagent. Either way, whatever the form of borane is, we should assume that it acts as BH3. Its formula is BH3 or this structural formula. So in a reaction with an alkene, borane adds to form alkyl borane. And stoichiometry is of course 3:1 because there are 3 BH bonds and each of those bonds can add across 1 pi bond. At the end we end up with trialkyl borane as the final product. Trialkyl boranes are highly unstable. They're actually pyrophoric. They would ignite spontaneously in the air, so we don't isolate them. Instead, we immediately oxidize them. So trialkyl boranes are oxidized with hydrogen peroxide. We add sodium hydroxide, small amount of sodium hydroxide, to the solution to make hydrogen peroxide more nucleophilic. and products are corresponding alcohols. So you can see that net result is overall addition of water across a double bond. Of course, when boron adds to one carbon of the double bond, and of course the other hydrogen has added to the other carbon. And so this would be hydrogen that originated from boron. Here are some examples. So this is 1-methyl cyclopentene. Hydroboration gives this alkyl borane. Only monosubstitution is shown here. Of course, trialkyl borane could form. And then upon oxidation, we end up with this alcohol, 2-methyl cyclopentanol. So you can see addition is anti-Markovnikov. So hydroboration oxidation sequence is method to add water across double bond in anti-Markovnikov fashion. The reason behind this observed stereoselectivity, and actually regioselectivity, anti-Markovnikov is regioselectivity, and you will see in a moment stereoselectivity, is in the transition state. So transition state is shown here in the middle. So borane reacts with carbon-carbon double bond, and these are the two possible transition states. And this transition state, shown at the bottom, where boron forms bond to more substitute carbon, is unstable because of the steric hindrance. If you look at this carbon with its substituents and then boron with its substituents, this looks like butane in eclipsing conformation. So very high torsional strain, very high steric strain. So this is highly unstable transition state. On the other hand, when boron adds to less substitute carbon, as in the top example and this top example, then there is this steric hindrance is minimized because large R groups are far apart from each other. So that's favored transition state, and for that reason, boron preferentially adds to less hindered carbon. And then upon oxidation with peroxide, that's where OH hydroxyl group ends up on this less substitute carbon. It displaces boron. And so that's why we end up with anti-Markovnikov addition. When it comes to stereoselectivity, both boron and hydrogen add from the same side of the double bond. That's so-called Syn addition. So Syn addition means addition from the same side. And then when boron is replaced with hydroxyl group, it's replaced with retention of configuration. So if boron was above the plane of the ring, then hydroxyl is above the plane of the ring, which means that two substituents, hydroxyl group and hydrogen, are added from the same side of double bond. So that's Syn addition, and that results, of course, in formation of cis product. Again, don't make mistake and assume or call this cis addition. It is Syn addition, but product is cis. And here is another example of anti-Markovnikov addition. It is possible to carry addition of hydrogen across a double bond in the presence of a suitable catalyst. On its own, hydrogen will not add to an alkene, but if suitable metal catalyst is added, then reaction proceeds quite well and quite readily. And suitable metal catalysts are noble metal catalysts such as palladium, platinum, or ruthenium. And also nickel works quite well. Nickel requires a little bit more vigorous reaction conditions, higher temperature and higher pressure, but it's inexpensive. So here are some examples. So for example, addition of hydrogen in presence of platinum catalyst, platinum dioxide, and the product is corresponding alkane. In general, hydrogen molecule adds across a double bond to give corresponding alkane. So note here palladium catalyst. So that's palladium on carbon. We write it as shown here, palladium-carbon or palladium/carbon. Metal catalyst is heterogeneous catalyst. It's added as metal itself. But reaction, as you will see in a minute, occurs only on the surface of the metal, which means that as solid metal is added, most of the metal does not participate in the reaction because it's on the inside of the bulk of the metal. The only relatively small proportion of atoms are on the outside. Even if we use fine powder, still most of the metal atoms are on the inside of those particles. To increase surface area of the metal, Sometimes we adsorb metal or apply it to some solid support. Common support is charcoal, carbon, and that's used here or in case of ruthenium. Another support is silica or silicon dioxide. Silicon dioxide is called silica. So those are common inert supports, and they are used simply to increase surface area of the metal. They don't participate in reaction in any way. And the last example is use of nickel as a catalyst. Here is reaction mechanism. So suitable metal is metal that has empty d orbitals and readily reacts with hydrogen in such a way that it homolytically breaks hydrogen-hydrogen bond, and that results in adsorption of hydrogen to the surface of the metal. Some of these metals can absorb so much hydrogen that they actually could be ignited once they have absorbed hydrogen. So these hydrogen atoms are now attached to the surface of the metal. There are, of course, a lot of them, not just one molecule, and they are free to move left, right, back, and forward in two dimensions along the surface of the metal. Then alkene also can attach to the surface of the metal. With its pi electron pair, it donates its pi electron pair, you can see here enlarged, to empty d orbital of the metal. And that forms initially a pi complex. So alkene metal pi complex. Next step that happens is that hydrogen takes the electron pair it was sharing with the metal and forms a bond with the carbon. So basically adds to carbon-carbon pi bond. That will force pi electron pair to move to form carbon metal. So it will move to the metal and will form carbon metal single bond or sigma bond. So now we have one carbon-hydrogen bond that is formed. Next step occurs so fast that there is no time for rotation about this carbon-carbon single bond. So in the next step, another hydrogen, so that means so fast after addition of the first hydrogen atom. So second hydrogen atom very quickly adds to the other carbon of the double bond and displaces metal free electron pair. The end result is that two hydrogen atoms, even though they add sequentially one follow the other, add so fast that rotation about carbon-carbon single bond does not occur. And that means that both hydrogen atoms add from the same side of the double bond, or addition is seen. We have already seen that form of addition. And as you can see, alkane now leaves the surface of the metal as the product, and it is interesting that it is in less stable eclipsing conformation. Of course, in the next fraction of a second, it will rotate about carbon-carbon single bond and assume staggered conformation. This reaction has numerous applications, and here are two. One of them is to estimate stability of alkenes. Alkenes undergo readily hydrogenation to be converted to more stable alkanes, which means that alkenes are unstable compounds. And degree of stability or instability is measured by their energy content. So unstable alkenes have high energy content and will release large amount of energy upon hydrogenation. Stable alkenes correspondingly have low energy content and will release relatively little, comparatively little energy upon hydrogenation. So if we can select series of alkenes which upon hydrogenation give the same product, then we can compare their relative stabilities. And this is the case here with a series of butenes, because upon hydrogenation all of the different butenes give the same product, butane. So we have a benchmark, same reaction outcome, so same energy outcome, because product has same energy in each case. So when we use different butenes, we can see that one butene upon hydrogenation releases 30.3 kilocalories per mole. That's a relatively large amount of energy. That one is the least stable of all possible butenes. Now you can see that two butenes release comparatively less energy. Cis-2-butene, 28.6 kilocalories per mole, and trans-2-butene, 27.6. Which means that more substitute alkenes are more stable compared to less substitute, and cis is less stable than trans. The reason for it is that cis isomer has two substituents in effectively eclipsing conformation, and they are close to each other, so there is steric hindrance. In trans isomer, those two substituents are on the opposite sides of the double bond, so there is no steric hindrance. So you can draw a conclusion that more substitute alkene is more stable one compared to less substitute, and trans is more stable isomer than cis. The reason why more substrate alkene is more stable is just like carbocations in hyperconjugation. So an alkene is stabilized through hyperconjugation with its substituents. Another common application of hydrogenation reactions is in determining nature of unsaturations, number and nature of unsaturations. So here we have several examples of compounds with 2 degrees of unsaturation. First compound is bicyclic compound, and it has 2 degrees of unsaturation, but it doesn't react with hydrogen. Of course, that's because hydrogen adds only across a pi bond. So since there is no reaction with hydrogen, we would draw a conclusion that both degrees of unsaturation are rings. In next 2 examples, we again have 2 degrees of unsaturation, but each molecule reacts with only 1 equivalent of hydrogen. Then we will draw a conclusion that one unsaturation is pi bond, the other one is a ring. Note that we don't know the ring size or where the pi bond is, whether it's inside the ring or outside the ring. We only know that there is one ring and one pi bond, but nothing else. And finally, in remaining 3 examples, we have 2 degrees of unsaturation, and in each case, each compound reacts with 2 equivalents of hydrogen, which means that there are 2 pi bonds. And product is, of course, corresponding alkane. But we cannot tell in any case what is the nature of those 2 pi bonds. Are they 2 double bonds? What are their positions next to each other or far apart? Or is it a triple bond? So as you can see, we can get some information about nature of unsaturations, but it's rather limited information. And now we are going to look at oxidation reactions. First, we are going to look at oxidation reactions that do not cleave double bonds. So in those reactions, addition occurs across a pi bond, while carbon-carbon sigma bond remains intact. So first such reaction is epoxidation, and reagent for such reactions is a peroxide. Peroxyacid, not peroxide, but peroxyacid. So an alkene reacts with peroxyacid. Note peroxyacid has this OOH functional group. So formula of peroxyacid, general formula is RCO3H or RCOOOH. So there is that weak oxygen-oxygen bond again, and that's peroxyacid. Peroxyacids are easily prepared in reaction of carboxylic acid, such as acetic acid and hydrogen peroxide. By mixing the two, we end up with peroxyacid, peracetic acid in this case, and that's suitable reagent. So here are some examples of common peroxides: hydrogen peroxide, alkyl hydroperoxide, dialkyl peroxide. So hydrogen peroxide would be reagent to make peroxyacid. Peroxyacids that are commonly used in these reactions are peracetic acid. This one is the least expensive and the most commonly used. Then metachloroperbenzoic acid is used if we need a mild reagent. So it's milder than peracetic acid. If we need vigorous reagent, then we use trifluoroperacetic acid. Here is the reaction mechanism. You can see it's concerted reaction. There is only there is only transition state, no intermediates. So no intermediates, only transition state, and this is transition state. So you can see all the bond formation and bond breaking occurs in the single step, and it's this end oxygen, this terminal oxygen, that is incorporated in the epoxide. Epoxides are compounds that have 3-membered ring. One of the atoms is oxygen. Byproduct, which we don't need, is carboxylic acid, so product is epoxide. Because reaction mechanism is concerted, there are no intermediates, there is no possibility for rotation about carbon-carbon single bond. And that means that reaction proceeds with what we call retention of configuration. So if starting material, for example, was cis alkene, product is cis epoxide. That means if substituents are on the same side of double bond, they end up on the same side of 3-membered ring. And of course, trans alkene results in formation of trans epoxide. Reaction is what we call chemoselective. Chemoselective means that reagent can make distinction between different functional groups. But for reaction to be chemoselective, we need to use the mildest possible reagent, metachloroperbenzoic acid. Here we have in this compound 1,2-dimethyl 1,4-cyclohexadiene. We have two double bonds, less substitute on the left and more on the left, and more substitute on the right. More substitute double bond is better electron pair donor, better pi electron pair donor, and so that's why that one reacts preferentially to less substitute. But to get selective reaction, so chemoselective, one functional group over the other, chemoselective means that one functional group preferentially reacts over the other. So to get that, we have to use the mildest reagent. If reagents were peracetic acid or trifluoroperacetic acid, then both double bonds would have reacted and product would have been diepoxide. Another type of reaction where addition across a double bond occurs is hydroxylation. Hydroxylation means addition of two hydroxyl groups across a double bond to two carbons of the double bond. Reagents for hydroxylation reaction are permanganate under mild conditions. Permanganate under mild conditions means, as described here, potassium permanganate in basic solution, for example, solution of sodium hydroxide, and at low temperature ice bath. Here it's indicated as 5 degrees Celsius. Product is cis product, cis dihydroxyl compound or cis diol. Cis product means that addition is syn. So stereochemistry of addition is syn, and product is that it is. Alternative reagent is osmium tetroxide, and then we have to carry out workup by using suitable reagent, and you will see that in a minute. Here are reaction mechanisms. Reaction mechanisms are very similar. In case of permanganate, we have intermediate. So intermediate is a five-membered ring, and this five-membered ring is unstable and hydrolyzes in presence of water to give cis diol. And you can see now why addition is syn. Both oxygens have to add from the same side because intermediate is five-membered ring. In case of osmium tetroxide, product is actually stable compound. So this osmate ester is stable compound and can be isolated. We don't isolate it, we actually decompose it. And suitable reagents to decompose it are, as in this case, sodium bisulfate, or we can use potassium hexacyanoferrate, shown here. We can use hydrogen peroxide, or one of the really good reagents is N-methylmorpholin oxide. N-methylmorpholin oxide is good because it will decompose this intermediate ester to give diol, but also it will reoxidize osmium trioxide back to osmium tetroxide. So in presence of NMO, N-methylmorpholin oxide, osmium trioxide is reoxidized to tetroxide, and it makes the entire process catalytic. Given that osmium tetroxide is volatile and toxic, that's really advantageous if we can carry out reaction under such conditions where we can use only catalytic amount of osmium tetroxide. And here are some additional examples that show that addition is syn to give cis product, and here it also shows that approach of the reagent is from less kindred side. So you can see that here we have double bond in six-membered ring, but this six-membered ring has bridge or two bridges. One bridge, this is better shown here at the bottom. So this is the same compound and the mechanism. So you see one bridge is smaller bridge, where carbon has two hydrogens, but top bridge is carbon with two methyl groups. You see, and those two methyl groups impede attack of reagent from the top. So reagent can come only from the bottom, osmium tetroxide, and so osmate ester forms only by approach from the bottom. And upon hydrolysis, two hydroxyl groups end up opposite from larger bridge. So steric hindrance plays a role, and approach is from less hindered side of the double bond. And finally, we are going to look at oxidation reactions that involve cleavage of the double bond, where both sigma and pi bond of the double bond are broken. One such common reaction is ozonolysis. Ozonolysis uses ozone as a reagent. So ozone has a molecular formula of O3, so it's allotropic modification of oxygen. Of course, ordinary oxygen is O2. These are resonance structures of ozone. You may recall them from general chemistry course. And so you can see from these resonance structures that in those resonance structures, one of the oxygen atoms is electron deficient. That means electrophile. So it's strongly electrophilic. Here is a reaction mechanism. So molecule of ozone adds across a double bond. See, electrophilic oxygen accepts pi electron pair from carbon-carbon pi bond, and the other oxygen, that is a nucleophile, nucleophilic oxygen. Here are two resonance structures. That oxygen donates electron pair to give first intermediate, which is called primary ozonide or molozonide. That one is unstable. You see it has two oxygen-oxygen single bonds. You know that compounds with one oxygen-oxygen single bonds are highly unstable, peroxides. So this one has two. This one is unstable. It immediately collapses or breaks up into two fragments by breaking of oxygen-oxygen single bond and carbon-carbon single bond. We end up with two fragments. One of the fragments is Zwitter ion. It has two ions within the same molecule, positively charged carbon, negatively charged oxygen, and we end up with carbonyl compound, carbon-oxygen double bond. One of those species flips, and then bonds are reformed. Flips 180 degrees, and bonds are reformed to end up with actual reaction product, ozonide. So this is the formula of ozonide. So you see original carbon-carbon, what used to be carbon-carbon double bond, has been replaced by two bonds. One that involves carbon-oxygen bond, and the other carbon-oxygen-oxygen bond. That ozonide is now immediately worked up. Reactions are usually carried out in solvent like dichloromethane. If you try to isolate ozonide by evaporation of dichloromethane, ozonides are explosive and actually product could explode. Instead, we carry out workup. Workup can be carried out under reducing conditions using sodium borohydride as reducing agent, and then products are corresponding alcohols. So each oxygen of the double bond, each carbon of the double bond ends up with hydroxyl group on it as an alcohol. So you can see that the double bond has been cleaved, and two fragments, this fragment on the left gives an alcohol, and fragment on the right also gives corresponding alcohol. Here we have another double bond cleavage, and again two fragments you can identify give two alcohols upon sodium borohydride workup. In a ring compound, upon cleavage of the double bond, we don't have two fragments, but ring undergoes ring opening to end up with two alcohols, or with diol, with open chain diol as reaction product. Alternatively, we can carry out reduction under bit milder conditions with zinc in acetic acid or with dimethyl sulfide. Either way, zinc, first and last example, or dimethyl sulfide, product is the same, corresponding carbonyl compound. So carbon of the double bond ends up as a carbonyl compound, carbon double bond oxygen. Again, double bond is cleaved, and each fragment gives corresponding carbonyl compound. So this is two carbon fragment, two carbon-carbon compound. Again, cleavage of the double bond and two fragments. Again, in case of a cyclic compound, cyclohexene, double bond is cleaved, but now we end up with open chain dicarbonyl compound. Third possibility for a workup is oxidative workup. Oxidative workup upon ozonization is carried out with hydrogen peroxide. So these are three examples with hydrogen peroxide workup, oxidative workup. In case of oxidative workup, if carbon of the double bond is monosubstituted, then product is carboxyl group, corresponding carboxylic acid. So this double bond is cleaved, and since each carbon of double bond is monosubstituted, we end up with two fragments that are two carboxylic acids. Since this fragment on the right already had carboxyl group, now we end up with dicarboxylic acid. So this second carboxyl group is a result of oxidation, cleavage of double bond. Here is another example, cleavage of double bond, and we end up with two fragments, two carboxylic acids. Note that if one of the fragments is just single carbon atom, then that one is oxidized initially to formic acid, but formic acid is unstable under these conditions and oxidizes further or decomposes to carbon dioxide and water. So it's carbon dioxide that is reaction product. So under oxidizing conditions, so ozonization followed by oxidative workup, single carbon atom, and there is CH2 group present. So we have CH2 group, so terminal double bond, that carbon ends up as carbon dioxide. Well, the other carbon, if it was monosubstitute carbon, will end up as carboxylic acid. If it's disubstitute carbon, then as you can see, for example, like from this example, It's just a carbonyl group. You cannot distinguish that from zinc workup. Ozonization has a limitation that because products are explosive and ozone is difficult to generate, we need ozone generator. Limitation of scale. We can carry out reaction at multigram scale, maybe 20 grams at the most. But if we need reaction at larger scale, ozonization is not suitable. One of the suitable methods is permanganate oxidation. So permanganate, but under vigorous conditions. You can see that permanganate under mild conditions. So permanganate under basic conditions and in ice bath resulted in cis hydroxylation or Syn Addition. But under vigorous conditions, and vigorous conditions difference is heat. Reaction is carried out in boiling aqueous solution. So it's still permanganate under basic conditions in sodium hydroxide, but in boiling solution. Then reaction outcome is the same as that of ozonization under oxidizing conditions with oxidizing workup. So double bond is cleaved, disubstitute double bond, disubstitute carbonyl double bond like this one, results in formation of carbonyl group, single carbon is converted to carbon dioxide. Rings are opened to open chain compound and each carbon of the double bond ends up as carboxyl group because this is monosubstitute carbon. Here we have another example. Again, double bond is cleaved. Monosubstitute carbon gives carboxyl group, single carbon, carbon dioxide. And note this is a bit unusual example. So this ring that is common to this double bond is common to two rings. When it's oxidized, we end up with dicarbonyl compound because each carbon of the double bond is disubstitute carbon. So permanganate oxidation results in same outcome, cleavage of the double bond, where single carbon gives carbon dioxide, monosubstitute carbon gives carboxylic group, carboxylic acid, and disubstitute carbon, carbonyl group. Same outcome as ozonization followed by oxidative workup. And this completes our study or lecture on reactions of alkenes.